Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Ladies and gentlemen, welcome back to another live stream. Alright, so I basically asked my Discord server members. So vote for tomorrow's live. Of course, this was yesterday. I asked them either to continue Codotaku dev, like the Codotaku engine that we're working on, try LLVM, absolutely no clue where to even start. Try compiling Godot from source, and the real challenge is contributing and continuing the custom C standard library. Because if you have seen yesterday, it was very clear that I needed to create my own kind of custom standard C standard library if we were going to be using C. So yeah, we're working on such a project. In fact, I have published that. Where is it? I forgot. I guess coding, yeah. There you go. I'm working with some other cool people. Like this guy right here. We have just started to work on it, but let me try to find the link real quick. And of course, please join my Discord server so you can get to vote and get notified. I'm not sure where is the link. Bruh. Alright, hold on. Let me go to my GitHub real quick. GitHub. Let's see, what did I even call it? I think I called it CDTK. Okay, cool. There you go. So I've just started work on this and opinionated the modern open source C23 alternative to the standard library, inspired by Ziglang standard library and the Vulkan API, platforms, Windows primarily, and Unix. And I may even remove Unix, but either way, for now, I think we're just going to try to make it work on both platforms. Otherwise, we're just going to focus on Windows. And then the compiler would be Clang 16, and contributions are very welcome, but make sure to use Clang format and CMake format. Okay, pretty much. So currently we have only implemented, I was so sleepy yesterday, so I only implemented one thing which I thought was super simple, which is a dynamic library, which just uses Lloyd library in Windows, and it uses in Unix, it uses DL open, as you can see. You could use it, for example, to load the Vulkan library or the math library, etc., and just get functions from it. That's pretty simple. And also, of course, I made the ground for some CMake setup, etc. And of course, well, where is it? Hold on, include. Here you go, the interface. And of course, the types. This is the first thing that I worked on, just defined some types. And this is actually, I should remove this. This is not needed in my case. But yeah, anyway, so that's pretty much it. All right, so let's go back to the real deal. So right now, what we want to do today is try to figure out how we can even start LLVM stuff. I have no idea. So today we're just going to see together how it's gonna go. I even have no idea what language we're gonna be using. And hello Ridwan Karti, welcome to the live stream. He's that guy that I talked about. Let's go. All right, so welcome. All right, welcome back. So let's see. LLVM. Let's look for an LLVM tutorial, some sort of thing. I don't know. Let's see, table of contents. Okay. Though I do have some very superficial information about LLVM just from dealing with other technologies, but I never really sit down and just tried to get deeper into it. So we'll see today. Alright, so my first language front end with LLVM tutorial. So basically there's documentation, there's getting started tutorials essentially. Uh-huh. Alrighty. So let's see. Welcome to the LLVM project. I really wanted to try LLVM for a long time now, and the compiler stuff in general. But we'll see. See like languages. And if you don't know, Clang LLVM is actually being used by all sorts of modern languages today, like C, C++ using Clang, like Rust, like Zig. All of these you are using the LLVM for the backend, for the code gen at least, and the optimization. So they basically, at least from what I know currently, they take their language, they convert it into LLVM IR, which is kind of like the cross-platform assembly, intermediate representation of LLVM essentially. And then LLVM takes care of going ahead and optimizing that cross-platform immediate representation or assembly kind of thing, and also takes care of the code generation to whatever target you want. Like, for example, you would tell it, please convert this LLVM IR, let's say to x64 Intel assembly or whatever. So yeah, check out LLVM, including sub projects like. So this is basically making. Working with assembly directly with one of the assembly languages, kind of a legacy at this point. So even if you want to work with assembly directly, you may probably want to just work with LLVM IR. Just type it out, I guess. We'll see. So, okay. The LLD linker and more. I don't think we can actually compile LLVM. It's gotta be crazy. I don't have that kind of computer. And it's also gonna take a lot of time. To save storage, check out time, you may want to do shallow clone. But what a shallow clone does exactly? Not sure. Anyways. Configure and build LLVM and Clang. Yeah, makes sense, because if you generate assembly directly, you need different versions for different yeah, pretty much. So you gotta learn all of those, which just doesn't make sense. Although still, if you want to like really know exactly how the actual bare metal works, then maybe you may find it useful to learn assembly directly instead of LLVM IR. But anyways, configure and build LLVM in Clang. CMake, some common build system generators, okay. I really wonder if I can really afford to compile this. Should we try that? I don't think we can. It's a very huge project. Try setting a basic CMake. I'm just skimming through this and just seeing what's going on, pretty much for now. There you go. Note that debug builds require a lot of time and disk space. We'll need about 3 gigs of space. A full build of LLVM and Clang will need around 15-20 gigs. It's gonna take years to compile. The exact space requirements will vary by system. It is so large because all of the debugging information and the fact that the libraries are statically linked into multiple tools. Oh my god. If you are space constrained, you can build only selected tools or only selected targets. The release build requires considerably less space. Though I did install LLVM before using Scope Package Manager on Windows, and also I have Arch Linux subsystem, so that could help, I guess. Let's see what I have. Okay, I already have some LLVM tools, seems like, just by doing scope install LLVM. Though of course before you could do that, you have to install scope, In fact, I have done it in one of my previous live streams, but there you go. This is pretty useful. Sometimes it doesn't work, but most of the times it does work. But anyway, so I guess at least right now we do have the LLVM tools. Right, the table below. Alrighty. So I think they're just talking about how you can build LLVM, etc. Though I wonder, I guess I just gotta take like binaries and use it in my project. Although I, sorry, kind of hate using binaries directly. But at this point, no way. It's like LLVM, bro. hmm Oh well. I've never worked with LLVM before, but I had heard the docs are so bad. I think it will struggle a lot today. I know. It was kind of like just like a joke of actually suggesting it here. But you guys, like 7 people, have chosen trying LLVM over everything else. So that's interesting. So we're just gonna shame ourselves today, and hopefully we at least can get something working. You know, it's like, bro, this is getting crazy. I know. Kyle, what is even that? How do you even spell that? Kaleidoscope language? Tutorial run through the implementation of a nice little compiler for a non-trivial language. Mm-hmm. Nice. Nice. Public include. Forgot about that there tutorial to look at. Yeah, that's probably what I'm gonna look into. The generic support libraries provided by LLVM. So seems like C++ have first class support when it comes to LLVM because pretty much I think it's being created with C++. So um, it's like I have a kind of like a love-hate relationship with C++. Like I see it being used in such a huge projects like LLVM, like in Real Engine, like Godot Engine. But at the same time, bruh, like I don't know. Well, but though they do take a lot of time to compile because of C++. Well, anyway, most source files are here. All right, so this is probably not very useful for. Oh, actually, this is useful. All right, so I really do need to know what are at least those tools are named. Oh, so you could actually use it with C, I believe, and other languages. Um, but I guess we're just gonna go with the one they recommend, which probably would be C++, at least for now. Um, Luck points, although I kind of hate C++, but anyways, there's C bindings for, I guess, yeah. But I'd like to basically go with the way they wanted you uh, to deal with it in the first place, which I would guess it's C++. So, hello, Marty Flowers, welcome back, welcome. Bug point is used to debug optimization passes. Write to compiler backend next. Rice 7th, welcome to the live stream. Oh well, we're gonna see. Today, I just want to try and see if I can even figure out to even create something just tiny, just something that works because I really don't know. We'll see. So this is the tools that are available basically. And oh, hold on, you can go. All right, fine. Ooh, all right, command guide. I'm more interested into the command guide too. But anyway, so bug point. What is bug point? Our code generation backends. All right, so there's call to prayer for now. I'm just gonna uh, mute for a second. All right, let's go. Um, so for now, we have found these resources which are interesting. So we can either go the command route, where basically we're using the LLVM tools, or we could go with the div route, which basically, trying to create a little compiler seems like. Um, what do you think? Bug point is used to debug optimization passes or code generation backends. Reduce an archive containing. I have no idea what they're talking about here. The assembler transforms the human readable LLVM assembly. Okay. Human readable LLVM assembly to LLVM bitcode. That's interesting. Assembly. Oh, this is interesting. Okay. The disassembler transforms the LLVM bitcode to human readable LLVM assembly. So this is basically the opposite. Reverse engineering. This has okay, so all right. LVM link, not surprisingly. Well, yeah, it's very clear. Link multiple LVM modules into a single program. Li is the L. Hold on a second. Alrighty, back. Okay, what is LLC? Is the LLVM backend compiler which translates LLVM bitcode to a native code assembly file. Which translates LLVM bitcode to a native code assembly file. So, you haven't pinged everyone. Oh my god. Oh. Oh my. Well, that makes sense. Thank you for letting me know. uh, I should surely annoy my members, of course. Hold on. Where is it? Let's see. Let me copy the video URL. Gotta wake him up. Uh, Alrighty. Pretty cool. Thank you, Ahmad, for letting me know. And welcome back to the live stream. Let's go. Alright, so I think we may just go with the route of trying to basically write LLVM assembly and trying to basically generate a executable from it, or at least an object file from it or something. I think that's maybe simpler. So we kind of like just learning assembly instead of right away going into trying to make our own compiler. So I think, what do you think? I mean, let me know. OPT reads LVM bitcode, applies a series of LVM to LVM transformations, which are specified in the command line. What? And outputs the result into bitcode of the program transformations available in LVM. So basically, I think that you could basically feed it with LVM bitcode, and you can choose what optimizations you can do on it, or at least what they're saying transformations. OPT. OPT can also run specific analysis on an input. LLVM bitcode file and print the results, primarily useful for debugging analysis or familiarizing yourself with what analysis does. Okay, I guess let's maybe try to just write some LLVM assembly for Hello World. I don't know how hard that would be. I have no clue, but I guess that's probably the way I'm gonna start with. So yeah. So what we need. So make a PHP compiler as PHP compiler. Oh my god. Oh well. LLVM link. LLVM AR. Nah. Like a Zig compiler would be better. The archiver. Dollar everyone. That's for sure. Okay, so let's see what we need now. The assembler transforms. So I think I'm gonna try to basically make human readable LLVM assembly because I'm not a machine. And I'm gonna convert it to LLVM bitcode. And then I'm not sure what to do next. LLC is doing which translates. Okay, so from LLVM bitcode we can pass it to LLC here, which would give us a native code assembly file. All right, so I think basically we'd need to use LLVM AS and then LLC after it, essentially. Does that make sense? All right, let me see if I have these tools. Hopefully I do. LLVM AS. What? Maybe I don't have them. Oh my god. Die, my favorite function. Ranlib, RC. What? I don't have it. Seems like. Interesting. Oh my god. LVMAS. Alright, let me see where I can find those tools. Doesn't seem like I have all of them. Let's see. We gotta be looking for maybe some binaries because surely I cannot compile those. Alright, what is going on here? This is a lot of stuff. Okay, LLVM dash 16.0. Okay, Win64, I believe. Is that the whole package? Yeah, I would guess so. Let me try it. Oh, actually, this is an exe. What do you mean? Well, let's just do it. Okay, let's see. I have no idea. Yeah, I guess it's maybe an installer, right? Okay, and this is gonna be interesting. Okay, just installed earlier. Let me see if it contains what you need. All right, installed it. Okay, let's see. All right, time of truth. Let's see if this is a compiler. I like if this is an installer. Uh, Otherwise, what could it be? There you go. Yes. Alrighty. It seems like an installer, right? Who reads the the terms of agreement, etc.? Did not add LVM. Oh my god. Add LVM, please. Please. Create no. Ready. Okay. I do. Not gonna lie. The audio stream current bit rates is lower than. Oh my. Hold on. Is the audio fine? Or YouTube is joking on me? The audio stream's current bit rate is lower than the current. Yeah, weird. Anyway. So, okay, it seems to be installing a lot of crazy tools right there. And oh my god, it may actually. I don't know how it's gonna deal with the other LLVM stuff that I already have installed. So, just to be safe, I'm gonna try to install LLVM that I installed with Scope, so I don't have some weird bugs. Well, how do you even do that? I never done that. Clean up by removing old versions. In install, okay. All right, let's go. It was that simple. Nice. Alrighty. So it does seem like it's installing a lot of crazy stuff there. Interesting. I wonder if I can get some nightly binaries somewhere for LVM 17. But anyways, let's see. Okay, let's figure out if we got now these tools. Okay, what we have needed? Hold on. What was it? LVMAS, right? Yes. We only have AR. What? Bruh. Hold on. So how can I get those tools? Interesting. Let's see. Program files LLVM. Okay, bin. These are all the tools. Can I look for AS? Nope. Nothing there. Bruh. So how can I get those tools? Are you kidding me? Compiler art. Oh, maybe Clang. Well, not Clang, but Could it be in Clang tools? Crazy stuff. Well, LLDB, LLVM project, third party. Yeah, it doesn't have LLVM AS. Interesting. Oh well, good old Google. Or you know what? Let me try this AI that I have in Brave here. How to install. Let's see if it is any useful. Let's see if AI can actually replace this or not. How to install LLVM AS in Windows. Let's see. AS installer, what? uh, download the LLVM from the official LLVM website. What? Really? LLVM sources? Bruh. Are you kidding? Like, I'm sure the AI doesn't know how much it takes to actually compile LLVM. Documentation, Clang tools. What the? Okay, so these are just the versions, seems like. Okay. Mm-hmm. Okay, Clang tools, extra. What? Not very useful. Okay, let's ask Google how to install LLVM AS in Windows. All right, let's see. Uh, Hold on a second. Let me try to find my developer tools. There you go. Let's see if it contains that, maybe. Let's see if it can help. It only contains AR. Oh my god. Let's go. Okay. Interesting. It doesn't contain it either. Unless maybe let's see Visual Studio installer then. Let's see. Modify. Let's see if we can find LLVM tools. Nope. Uh, nope. Doesn't seem like so. Interesting. Where is this stupid LLVM AS? How to stupidly download this? Oh my god. Hold on. Let's pull up at least our Linux subsystem. And let's at least see how we can do that. Because it just doesn't seem like there's no resources at all about how to install it. Unless maybe if I actually really good need to go ahead and basically build a LLVM for that. Well. Okay, let's see if I have LLVM AS. And come on, why is this slow? Bruh. Try dash dash version. Yeah, that's true. Yo yo man 3D, welcome to the live stream. And I guess I do have it after all. Interesting. At least in my Arch Linux. I think it comes with the LLVM package, but okay, let's see. Dash help. Alright, let's go. So I have it in my Arch Linux subsystem WSL thing. Well, at least that's something, but I'd like to actually install it if I can. But at least right now we have a way out if we couldn't in Windows, but there you go. But I'm just very... what? LLVM config does not exist in Windows pre-built live binaries. You need to compile from the source code to get it. Huh? I would guess it's probably the same stupid thing with LLVM AS. Bruh. Anyway, let's just use the WSL for now at least. Okay. It shouldn't be too different anyways. So do I have Vim? Yes, I do have Vim. Alright. Well, let's see. Or we could actually work with code. We could work with code. Hold on. Within the WSL basically. But here you go. Arch Linux WSL have saved the day. Let's just close this. And let's try to connect with the alright, I'm already connected with the WSL Arch Linux distro. And what we're gonna do now, we're going to create a new folder, I think, right? Let's create a new folder. Well, what I have here. Okay, mkdir. Let's, well, LLVM learning. Alrighty, okay. Let's see if we have some LLVM assembly thing that could help or something. LLVM assembly? Well, LLVM IR, right. Cargo init win. Not yet. I think I'm gonna start with basically trying to use the LLVM tools instead of going right ahead and trying to make a whole bloated compiler. So yeah, we're gonna basically try to essentially first of all write some LLVM Hello World assembly, if possible, of course. I have no idea. We'll see. So LLVM IR language support, nice. This or this? I guess this is just syntax highlighting, yeah. But this, I guess, is a whole LSP, right? Interesting. Okay, install this guy. And yeah. All right, so LLVM IR extension. I have no idea. It does matter because that's what we used to actually like the plugins identify with that. The answer to answer more directly, the traditional extension is .ll. However, some tool chains want to treat the same as assembly file and hence prefer to use .s extension. All right, let's go with LL and try that out. And let's open code inside this folder. And let's find out. Okay, I guess. Well, not even Hello World. Just the most minimal assembly program ever. Minimal.l. Okay, it's identified it as LLVM Now let's find out how in the world we can program in this assembly. Okay. Well, what happens if I just feed it with this file, by the way? LLVMAS minimal.ll. What the? Huh? It gave me this stupid file. Minimal.bs. BC. Oh, well, it's not displayed in the text editor. What is that stupid BC file? No way. BS. So true. Oh my god. Well, let's see. LLVM bit. Oh yeah, makes sense. LLVM bitcode. All right, so we got the LLVM bitcode. Now I guess we gotta try to return it into native assembly or whatever. So I believe there was another tool which we have seen is LLC, right? Yes, LLC. Okay, let's try it out. That would be interesting. LLC minimal.bc. What the? I don't have LLC. Are you kidding me right now? Are you kidding me? LLC. What the? No way. Oh, it's maybe called just LLC, right? I have no idea what are these names. Programmers are the worst in in making names up. All right, so I do have LLC. It's just not starting with LLVM, which is interesting. So minimal.bc. And we got minimal.is, .s. Okay. Okay. So pretty much we have compiled our first LLVM We have turned it into a native assembly, I would guess. And of course, it's pretty much empty. .text, .file, and .section. I have no idea. The stream is done. Goodbye. Oh well. Alrighty. Well, minimal.ll.bc. So okay, but what's next? Okay, we have this assembly, but what we gonna do with it? I guess LLD. No idea. Not LLD, or maybe I should install it. But how do you actually turn assembly code into a binary? I would guess you basically link it, right? Ooh. There's also an interpreter. Hold on. So LLVM this, we could give it an LLVM bitcode and it would give us back. You can use Clang for that. No, you can for objects files. I don't know about assembly files. Yeah, I would get, that's probably what I think it would be. You would just link it with some C file, for example. Actually, hold on. I mean, what's gonna happen if I actually pass it to Clang, for example? What? In defined reference to main. Let's go. So in defined reference to main. Nice. But what happened maybe if I created maybe a C file and then try to link with it or something? I don't know. But well, Okay, let's try it out, I guess. Main.c, int main, just like that. And let's actually compile that. Clang main.c, and maybe I also would pass that. Oh my god. Can you choose the assembly arch, or architecture? You probably can. There's like no way. You probably can, right? Whichever assembly you want in the world. That's what's nice about LLVM. It's cross-platform. You just write LLVM IR, and then you could basically turn it into whatever assembly you want, I think. All right, pretty much we got. We basically have used main.c with minimal.s, and of course main.c have a main file. But right now let's try to make a standalone program, hopefully, with a main thing, right? So let's see. So for now I'm just gonna remove main.c. I'm gonna remove a.out. Alrighty. Now minimal.bc, minimal.s. Okay. So now let's try to write some LLVM IR stuff. All right, well, where can I find it? You can compile C code to LLVM-IR. Oh, how? I mean, I do remember that I can, but, and it should be with Clang, but I don't know how. It's probably some flag. So Clang C to LLVM. Oh, actually, that is a very genius idea. So I would just see how a C program would translate to LLVM IR and try to learn from that. Right, that is very good. Make it eval 1+1. There is a flag for that. I can't remember. Yeah, exactly. Dash emit LLVM. Okay, let's try that out. That would be very interesting. Very genius idea. So we're basically just gonna use Clang to generate LLVM IR from C code and just learn from that, basically. See how the compiler does it. So Clang main.c, but I do need some C file. Main.c. And what happens though if I feed Clang with an empty C file? No idea. But let's see. Dash emit dash l dash LLVM, I guess. Cannot be used when linking. How do you just compile an object file though? Clang pal obj. So it's basically trying to link it too, but I don't want to link it. Oh, I think that's C. All right, let's go. And we got main.bc bytecode. Nice. But we got bytecode. We didn't get .ll, which is basically human readable assembly, right? But what we could do, we could use that LLVM this that I can remember, hopefully, and we can pass it main.bc. And we get main.ll. Oh my god. There you go. There you go. So this MTC program, we have basically used Clang to compile it to BC, to bytecode, to LLVM bytecode, and then we used this Clang this LLVM dash this disassembler basically to disassemble that bytecode back to what is it called, to human readable LLVM. And I have no idea what I'm seeing here. What is even this? Module ID main.bc. I would guess this is a comment. Source file name main. Oh, yeah, it contains debug symbols, I guess. That's probably what this is. Maybe. Anyway, target data layout. Target data layout. What is even that? No idea. Target triple. What's this? LLVM.module.flags. What the in the world? LLVM.identifier. I would guess that's an identifier. Oh, I think this is probably supposed to be variable names or something like that. But it is just numbers because we have just basically disassembled already compiled bytecode or something like that. Basically, it doesn't contain those variable names essentially. So it's just numbers, I would guess. That's why. But this is probably supposed to be variable names, I guess. So I32, so integer, I guess. I don't know what these means. And W char size, I32 4. Pick level, P high level, UW table frame pointer, Clang version 16. All right, let's try to basically right now actually go ahead and say int main and just do that basically, and let's just say Clang and LVM disassembler, and let's see now. Okay, so something got added now. This is basically a hello, well, not hello world, but just a program with the main function. So basically same thing. I would guess these just debugging stuff. Function atters. No inline. Oh, attributes of function. But I would guess these are just comments, right? No inline. Define is how you define functions, I guess. Yeah, pretty much seems like. No inline, so I guess it didn't inline it. No inwind. Opt none. I would guess optimize none. SSP strong, EW table. Attributes 0 equal no inline. What is even that? Stack protector buffer size, target CPU, target features. Tune their CPU equal generic. And we have basically the same stuff that we had before. I would guess this is just like a footer kind of thing and this is header, but the actual relevant code is basically, I would guess this stuff. So it's defining, I guess, a function and DSO local, no idea what's that. I32, I would guess maybe this is the return type. This is main, basically the name of the function, I would guess. And I have no idea what 0 is, but I can see that maybe these are relevant. Maybe these are linked together, like, I don't know. And here it's returning an I32 0. Yeah, return I32 0. That is very interesting. All right. Now let's try to do something even more crazier, which is basically main, well, print f, you know. Oh well, it's gonna be bloated. Let's try just puts, which I would guess it's a little bit more simpler, right? Maybe, or maybe just exit actually. Yeah, just exit. Can we do that? Let's see, exit 0. Just do some math expressions. Actually, that's true, but the problem with that, I think it would optimize it out. The problem with that, I think it would optimize it out. Yeah, I would guess I would like it's such a simple optimization, so I don't think that would work out. Anyway, let's just try to say exit 0 and see what it's gonna do. Quick fix. Don't include the stdlib. The output will be bloated. I mean, let's see. Let's see. Let's see what's gonna happen there. Because, well, we're gonna have to do that anyways. But we can actually use assembly, but well, no, I don't know. We'll see. LLVM-this main.vc. Okay. Well, not too bloated. I would guess a lot of things have been compiled. It's not that bad, yeah. Okay, so what have changed? Pretty much as you can see, this haven't changed. This also haven't changed, I would guess. these kind of have changed. Like I think there was only one attributes section before. I would guess it's probably was this one, attribute 0, but then maybe these two guys have been added. Right. And this function enters no return, no inwind. Okay. Hold on a second. Oh, never mind. Okay, so here it's declaring some void exit. I think this is for the linker basically. It's telling the linker that there is maybe some external function, I would guess, that we have to link exit and one. It's using these attributes, I would guess. Okay. Of course, these didn't change. And now what's about this one? Still DSO local, same thing. Okay, so one, I would guess this is meant to be an actual variable. Yeah. And alloca. Oh, I32 align 4. So it's, I would guess it's allocating an I32, like an integer with an alignment of 4, of course, because, well, an integer size is 4. And it's trying to store an I32 0 in PTR1. Oh, in address, I guess, of this variable. It allocates in the stack. That's what I would guess. Yeah. Oh yeah, alloca. I remember. I remember even in C you have like that alloca that you could use it to basically, uh, you know, use it to, yeah, allocate an array into the stack. But it's, people really frown upon it. They never really use it to do that because you could basically blow out the stack. But yeah, it's being used here, right? So store I32 0. So it's storing 0 in this variable. And it's calling void exit. So it's calling this exit function with an I32 no in the 0. And this 2 here. No return. Ooh, no return. I guess it's storing in a register or something. Nah, not really the register though. Well, at least for this one. This one seems to be doing it in the stack. And basically using the pointer to that variable to write into it a 0. But here, I'm not sure. Maybe it would pass it into a register. I don't know. But basically, and here as you can see, unreachable, because exit is basically no return. Once you call exit, well, you just never get control back. 0 maybe mean the first register. What? IDK. Okay, so that's pretty interesting. I guess I'll just try to change the exit code, for example. And let's see. So as you can see, it just have changed this value pretty much. So we can already make a little compiler that basically returns, that exits with some sort of value. Pretty much. So, okay. Now let's try something more complex. Like, I would guess print, not printf. Let's just go with puts. Although, even if you use printf, I would guess it would compile it out. Let's first try puts, which is very simple. It just takes one single stupid string and it outputs it. Okay, pretty cool stuff. Call to undeclared function. Let's remove this as cdlib. Hello, HGKL. Welcome to the live stream. Okay, let me just actually do this in one command, LLVM this main.bc. Let's make a little script here. Or no need, actually, no need. Anyways, so let's see right now the actual, well, where is it? Main.ll. Where's everything now? All right, interesting. So Okay, so we have something new now. We have this .str here, which is private and named addr constant 14x i8. Well, I would guess i8 they mean the character basically. It's like a character, a char is i8, 8 bits, 1 byte basically. 14, I would guess that's basically how much characters there is. Byte, yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. Yeah, 14. And this is the null byte, align 1, because, well, it's actually 1 character. So, okay. Function attributes, no inline, no inline, blah, blah, blah. Function main. And it's basically, I would guess it's making a variable, maybe. Or register, possibly. I have no idea. Anyways, so call oopsies, what I have done here. Call i32 puts ptr no indef variable. So it's calling the puts function, which is just external external function. It's probably, with the libc, essentially the standard library. So call i32 puts ptr no indef, and it's passing it this guy, as you can see, and it's returning i32 0. I'm not sure though why they do need to every time just give it the type again, although, well, the compiler does have access to that anyways. But yeah, that's just how it works, I guess. Interesting. That is very interesting. Very, very interesting. Well. Now I'd like to try something crazier, which is to try to do some optimizations and see how that would affect it. Now let's try LLVM OPT maybe, and let's try on the main.bc, the bytecode. Oh, not found. What? Maybe it's just OPT? Main.bc. You're attempting to print out a bitcode file. What? Okay, hold on. Let's go back to, where's RD LLVM? OPT, yeah. It reads LLVM bitcode. So what's happening here? I have no idea what it's talking about. I'm just trying to optimize. But anyways. Okay, let's see. Something else, I guess. Okay, static compile. So what am I using, by the way? Hold on. Okay, let's clang. Let's pass it some flags and see how it goes. -03, for example. And this is what happened. 03, optimization. What about 02? Would it change anything? Didn't seem like. What about 01? What? Didn't change anything either. 00? It did. So in this simple case, 01, 02, 03 are pretty much the same exact thing. But 00 is different, of course. So yeah. Okay, let's see what we have done now. It's using this tail thing, tail call. Yeah, it's basically doing a tail call, right? Yeah. Puts ptr no indif non-null dereferenceable. What the? Dereferenceable. No capture, read only. So it's basically pulling some more tricks right now. Local and named addr. What? This is very interesting. What we should try next? Let me know what we should try next. This is very interesting. Alrighty. What we should try next now? Let me know. Maybe printf. Let's try printf. I would guess it would compile this out though. It would compile it to puts basically. It would optimize it to puts. Let's see. Alrighty. And let's turn off optimizations for now though. And let's see what's gonna happen here. And yeah, right now it's actually calling printf directly with no optimizations. And right now, as you can see, we have another string which contains the format. Cool. Call i3 ptr printf. Okay. And what if I actually right now try to optimize with O1? Didn't change, did it? No, it did actually change, but it still didn't actually optimize out the printf, by the way. Interesting. What if I do O3? Oh my god, it didn't actually optimize out the printf. Interesting. I would thought it would. But there you go, it doesn't. So when you don't want a format, make sure to use puts. Well, at least with Clang. So yeah, pretty much. Pretty interesting. Okay, what if I passed it some more stuff maybe? Stir one. Okay, that is pretty interesting. What do you think, guys, should we try next? This is very interesting. Compatible library tool for creating libraries for Darwin. LLVM bitcode linker. Hold on, let's go back to that place. So we have used LLVM AS. We have used this. Follow their tutorial maybe. Well, it would actually not teach me LLVM IR, I believe. It would actually try to make me use their LLVM directly, basically. I would guess, but well, we'll see. LLVM link, not surprisingly, links multiple LLVM modules into a single program. Is the LLVM interpreter, which can directly execute LLVM bitcode, although very slow for architectures that support it. Currently x86. By default will function just as a just-in-time compiler. So you can even make a GIT using LLVM, interestingly. And we'll execute the code much faster than the interpreter. Okay, LC, so we have used this one. Who's wild enough to code in LLVM IR? Probably me in the future. OPT reads LLVM bytecode, applies a series of LLVM to LLVM transformations, which are specified. Okay, can I actually say now OPT-H? Let's see what you have there. These are all the transformations we can apply, basically. What? I didn't understand a single word here. Bruh. O0, O1, O2, okay. Well, at least I understood something. Like O2, but science conscious. Write output as LLVM assembly. Okay, now what if I want to, let's say, compile to another architecture? Hold on a second, we didn't actually turn it into assembly, did we? No, we didn't. Interestingly, I still haven't done that. All right. Well, how can do this? I forgot. LLC, isn't it? Yeah, probably LLVM LLC. Actually, it's LLC, right? So what if we give it this main.ll? We get main.s. And there we go, we got native assembly. Very nice. Very, very nice. And what it was, hello world, right? Well, honestly, let's just go back to return, well, nothing basically. So let's go ahead and see the assembly that is generated, native assembly. I'm a bit familiar with the native assembly though, not much. But yeah. So here's the deal. I'm gonna use that kind of command, and then I'm also gonna chain the other command, which is llc main.ll. Okay, pretty cool. Main.ll. Okay. Okay, let's go. So this is basically just a program with the main function. .text section .file .global main begin function main p2 align 40x90 type main function. CFI start proc bb.0 XOR L. So it's basically XORing the registers AX, EAX, so as to get 0 in that register, and then ret Q. I'm not exactly sure what Q means, but at least return basically, well, return. So lfunc end size main. All right. Okay, cool. Cool. So what if I actually said clang main.s? Now I got a.out. And yeah, I just returned nothing, of course. So let's actually also add that. Why not? Clang main.s. Let's go. All right, now let's try puts hello world. Well, yeah, pretty much, right? And let's add cdio. And let's see what's going to happen here. So go back to main.s. And that's basically what you have done now. Okay, so l.str ASCII z hello world size lstr 14. All right, push q, so it's using the stack here, of course. rax, so it's pushing the register rax, the value in the register, I guess. Move l, so str is equal to ADI basically. Call q. Okay, it's calling puts, the extern function puts, and then XOR. Yeah, I just remembered now. I think L is meant to be maybe long, you know, some type basically, and Q is meant to be maybe quad if I remember. But anyways, RCX CFI ret Q. Okay, pretty interesting stuff. All right, so what next? Let's see. And by the way, let's try to run this, by the way. Linker command failed with exit code 1. What? Why? Failed to set dynamic section sizes. Bad value. Huh. Why it didn't work? No idea. Recompile with -fpi. What? Weird. But anyway, I think maybe let's try right now the tutorial that they, or maybe let's try to find some sort of, possibly some guide or something. I don't know. Let's see. But at least we have figured out some things, so that's nice. So what else? So these are basically documenting all the stuff that you can. Interesting. Bitcode linker, MCA, OPT. Alrighty. Convert addresses into source code locations. Ooh, you could probably use this for a debugger. Maybe. It would convert addresses into source code locations. LLVM optimizer, automatic test. Demangler. Print strings. Object strip into. Oh, okay. You could actually strip. Hold on. If I say, well, what is it strip exactly? Hold on. Object. Not sure what you're supposed to give it, but if I say, for example, main.ll. No, it's not a valid object file. Okay, so I guess you would basically, well, what about BC? No, it should be an OBJ, I believe, right? Yeah, makes sense. Okay, anyways, I think right now let's try the actual my first language front end with LLVM tutorial. Okay, this is interesting. So let's delete all this trash right now. RM, well, it's just much easier to just do this, I guess. Okay, let's try right now to make our own first own compiler. So, okay, pretty cool. What's going on here? Seems like it's not liking it. Okay. Okay, pretty cool. So let's see. So I have a lot of reading to do right now. Welcome to my first language front end with LLVM tutorial. This tutorial does not show best practices in software engineering principles. Every tutorial ever. For example, the code uses global variables pervasively, doesn't use visitors, etc., but instead keeps things simple and focuses on the topics at hand. Okay, this tutorial is structured into chapters covering individual topics, allowing you to skip ahead as you wish. Structured into chapters covering individual topics. This shows where we are going and the basic functionality that we want to build. A lecture is also the first part of building a parser for a language. Okay, they're using C++, so we're going to be using C++. And we use a simple C++ lecture, which is easy to understand. I mean, C++ and easy to understand doesn't go together. Is that okay? Implementing a parser and an AST. Implementing a parser. AST construction. It's Nice. Code generation to LLVM IR with the ST ready. We show how easy is it to generate LLVM IR and show a simple way to incorporate LLVM into your project. Very nice. Adding GIT and optimizer support. Did you guys understand so far something? One great thing about LLVM is it supports for GIT compilations. 3 lines to add GIT support. What? And later chapters show how to generate O files. I would guess object files, right? Extended language, control flow. Okay, so basically the first language doesn't gonna have control flow, but then in this chapter they would add it. If statements in the for loop. This is gives us a chance to talk about SSA construction. What is even that? The control flow. Extending the language, user-defined operators. Okay, we're entering the C++ territory right now of operator overloading, and everything is a class. Anyways, this chapter extends the language to let users define arbitrary unary and binary operators with assignable precedence. What? This allows us to build a significant piece of the language as library routines, okay? Usable variables. User-defined local variables along with an assignment operator. SSA form in LVM. LVM does not require a front end to construct SSA form in order to use it. What is SSA form? Bruh. Static single assignment form. What? That requires each variable to be assigned exactly once? Is this just a fancy term for declaring variables? No idea what they're talking about, but anyway. Okay. Let's go back. Where I was? Okay, here. Compile to object files. This chapter explains how to take LLVM IR and compile it down to object files like a static compiler does. And then we have debug information. A real language needs to support debuggers, so we add debug information that allows setting breakpoints in kaleidoscope functions. Print out argument variables and call functions. Conclusion and other tidbits. Wraps up the series by discussing ways to extend the language and includes pointers to info and special topics like adding garbage collection support. What? Exceptions? Are you kidding me? Debugging support for spaghetti stacks. What is even that? No idea. Etc. By the end of the tutorial, we'll have written a bit less than 1,000 lines of non-comment, non-black lines of code, long lines of codes. This is a Vulkan moment. With this small amount of code, we'll have built up a nice little compiler for a non-trivial language, including a handwritten elixir, parser, AST, as well as code generation support. Pretty interesting. Meanwhile, using 1,000 lines of code, you may just create a triangle in Vulkan. Oh my god, both static and GIT. Pretty cool. Okay, let's find out. Let's go. Chapter 1, the Lexer. So the kaleidoscope language. Meaning beautiful, form and view. Use conditionals, math, etc. Okay, GIT compilation of the symbol command line interface, debug info, etc. Pretty cool stuff. You want to keep things simple, so the only data type in kaleidoscope is the 64-bit floating point type, aka double in C parlance. Doesn't require type declarations. What? Okay. Seems like Python. This gives the language a very nice and simple syntax. For example, the following simple example. Computer computes Fibonacci numbers. So def fib x, if x is less than 3, then 1, else fib x minus 1 plus fib x minus 2. Pretty cool. Well, we also allow to call into standard library functions. The LLVM GIT makes this really easy. This means that you could use the extern keyword to define a function before you use it. This is also useful for mutually recursive functions. For example, extern sign what? Mutually recursive function. What does that even mean? Extern sine, cosine, and atan to arg1, arg2. And then use atan 2 with sine and cosine. Okay. Interesting. Where we write a little caloscope application that displays a Mandelbrot set at various levels of magnification. Let's dive into the implementation of this language that displays a Mandelbrot set. Okay, cool. So the lexer, when it comes to implementing a language, the first name. Okay, the lexer returns tokens from 0 to 255, I guess. What this even means? If it is an unknown character, otherwise one of these four known things. Toke eof, end of file, I guess, -1. Commands toke def, -2. Toke extern, -3. And toke identifier, -4. Toke number, -5. Okay. Static std string identifier str. Filled in if toke identifier, filled in if toke number. Lexer basically convert the input string into an array of tokens that can be easy to work. Yeah, I did actually make such a thing before, but with an interpreter though. It was pretty simple. Nothing. It was nothing crazy. But yeah, each token returned by our lexer will either be one of the token unknown values, will be an unknown character like plus. Oh, so that's what they mean by 0 to 255. So it's basically one of these guys, or they would return the ASCII character, essentially. Okay. Which is returned as its ASCII value. The current token, it's pretty genius idea. Okay. The current token is the identifier. The identifier str global variable holds the name of the identifier. So instead of having a payload or whatever, your own tokens would be just negative values, and you would basically use the range from 0 to 255 for ASCII value, essentially, for the unknown stuff, the unknown characters, which is interesting. Okay, if the current token is an identifier, the identifier str global variable holds the name of the identifier. If the current token is a numeric, literal like 1, non-value holds its value. We use the global. Yes, I do that too. It's a cool trick. Yeah, seems like we use global variables for simplicity, but this is not the best choice for a real language implementation. Yeah, we use global variables for simplicity. Makes sense. You can tell that whoever wrote this tutorial is very careful with global variables before someone follows him to his home to assassinate him or something. Because he's using global variables. Like every time he said, bruh, global variables shouldn't be used. We're just using them for simplicity. Interesting. Okay, the actual implementation of the lexer is a single function named getToke. The getToke function is called to return the next token from global variables for the win. Yeah, I pretty much never used global variables for a long time now. I don't know. The actual implementation of the lexer is a single function named getToke. The actual implementation of the lexer is a single function named getToke. Single function named, okay. I use them if I want something done quick. I see. getToke returns the next token from standard input. Static int getToke. Static int. Oh yeah, static variables. Let's go. Static int last char. Last characters. Skip any white space. While is space last char. Last char is equal get char. What? While is space. So while there is while the last character is a space character, get the next one. Oh, I see. He's basically skipping white space. Oh my god, I didn't see the comments. I feel like a machine right now because I skipped over the comments and I just have read the code instead. getToke works by calling the cgetchar function. So why use C++? Just use C at this point. Yeah, I mean, he's not even using enum class. He's not using... Well, anyway. getToke work, okay. To read characters one at a time from standard input. To read characters one at a time from standard input, it eats them as it recognizes them and stores the last character read but not processed. Last char. The first thing that it has to do is ignore white space between tokens. This is accomplished with the loop above. The next thing it took recognizing. If it's alpha, so if it's an alpha numeric character, then identifier str is equal to last char. Okay. While is alpha numeric, last char is equal get char, identifier str plus equal last char. Okay, so he's buffering those characters into that global variable. Okay. And after that he's checking if it is one of the keywords. Interesting. Pretty simple, pretty straight to the point. No magic there. So why not use else if? Yeah, why not use else if? Anyway. Note that this code sets the identifier str global whenever it elicits an identifier. Also, since language keywords are matched by the same loop, we handle them here inline. Numeric values are similar. If is digit or last char is equal to a point or dot, whatever you want to call it, std string num str, do num str plus equal last char is equal get char. While it is a digit, and yeah, interesting. Num value, and then it's using str2d, which basically is a string to double. .cstr. He's basically using C++ without using C++, just for a few things like string, for example. Yeah, pretty much. Okay, this is all pretty straightforward code for processing input. And reading a numeric value from input, we use the cstrtod function. He will be using CPP stuff later. I see. I'll probably regret why I'm trying to make him use C++ at this. Anyway, this is all pretty straightforward code for processing input. When reading a numeric value from input, we use C. Okay, sufficient error checking. Of course, it will incorrectly read. Comment until end of file. If last char is equal to this guy, then comment until the end of the file. Get char while cool. We handle comments by skipping to the end of the line and then return the next token. By skipping to the end of the line, okay, the next token file name the input doesn't match one of the above cases. Mhm. Don't eat the AF. If last char is equal AF, return toke AF. Mm-hmm. Yeah, I'll probably over-engineer it when I code it myself. Next, we'll build a simple parser that uses this to build an abstract syntax tree. We'll build a simple parser that uses this to build an abstract syntax tree. Next, we'll build... Okay, yeah, that will include... Sometimes my brain just lags and just like foggy, you know? It's like I'm reading, but I'm not reading the same. When we have that, we'll include a driver so that you can use the Lexer and parser together. Okay, let's try to make our own Lexer, though mine would probably be over-engineered as always. Unless if it didn't work out, then I'm gonna go with this simple way. I'm just gonna copy the code. But yeah, let's see. Let's see. All right. Okay, so how I'm gonna deal with that then? Let's see. Okay. Extern. So we have this guy. Okay, where to even start? Okay. I guess CMake quick start. Oh well, the Clank 16. Just copy stuff to save time. We'll see. The kit Clank 16.0.6 references a non-existing compiler binary. Oh, remove it. And hold on, I need to figure out... I do have Clang now, no? I do. Okay, never mind. So CMake quick start, scan for kits just to make sure. Because I have reinstalled LLVM, so who knows, it may... Actually, did I? I'm not sure. Anyway, never mind. Oh, it was probably talking about scope, maybe? I don't know. Anyways, CMake quick start, and let's see. So, Clang. Clang. Linux GNU. Okay, go with that. And enter a name. I don't know, LLVM learning, I guess. C++ project, executable. Let's go. CMake dash, well, CMake dash dash version. Okay. Let's go. Add executable. Project. Project name. Remove this chunk. And remove this from here. Use target sources instead. And also, let's add our crazy stuff. Target compile features. Gonna go with CXX CD23, I believe. And target, oopsies, what's happening here now? Anyway, so target compile options. And as always, I like to go with -w everything, -w error, -w if error limit, I think, or something like that. I don't know. Anyway, we'll see. Other than that, is there anything else that I'd like to add? Target set options or properties or something. Yes. And then project name properties. CXX standard CXX. What else? Yeah, extensions. And okay, I think that's pretty much it, all we need. Maybe. So let's see now. Okay, cool. So we're set up. Now let's try to basically copy this. Okay, so enum class. But yeah, we cannot actually use enum class. Okay, let's just copy stuff. Fine. Well, analysis, since we're just gonna copy stuff, let's just remove this for now. Although, well, yeah, it's just gonna take a lot of time, honestly, right? So, okay, pretty cool. So let's just copy stuff for now. Later on, maybe we could try to do it ourselves. Just to... Oh, I see. Skip any white space. Alrighty. Fizz digit. Flash char. There you go. Is that it? Oh, it's actually, they do already have the full code listing here. Okay. All right, where's the code listing that they're talking about? Oh, this is the actual full code that we're gonna write. Well, we're gonna copy. Okay, interesting. So we could basically reference this when needed. They're including debug symbols, O3, full optimization. They're calling it toy. Oh, well, interesting. This is just a toy for them, for whoever ever wrote this. CXX flags. Okay, pretty cool. So let's go back now. And let's see if this actually works, is it? How can I check? Let's see. So what we have done so far, we have this token here. We have identifier str num value. This would return the next token from standard input. Okay, we're skipping white space. And here, if is digit. Whoever wrote this probably can make a simple compiler in 1 hour. Yeah, I mean, it makes sense as he's calling this file toy.cpp. Oh, well. This is just a toy for him. Interesting. Okay. If it's digit, last char, cd string, num str, new, well, is digit. Okay, so it actually returns the type of the token. Okay. Flash char. Though, hold on. Oh, it's actually taking it from, yeah, from the command line input. Okay, interesting. So let's try to run this now. What? Oh, I see. So let's try to get the next token, I guess. Printf, I guess D, N. Okay. And here I gotta write something, for example, hello, and it says -4. Token identifier, nice. And if I say, let's say 100, whatever, minus 5, which is a number, nice. And def, let's see about that. Def minus 2. What about extern? Minus 3. And af, I would guess maybe writing nothing would give that. Actually, I cannot write nothing in the command line at least. So yeah. Anyway, you first try, Pog. Well, I just copied the code, so that makes sense. Well. Alright, so that's pretty much it. Now we could make this even crazier by just too simply saying, well, I guess while true, so we could keep on getting some input essentially, and we could say switch on get toke, and basically if it's, for example, in case of if it is toke identifier, for example, then we could basically printf identifier str. Oopsies, let's just use stdc out. I have no idea what I... Okay, so stir identifier, right? Okay, pretty cool. So that's identifier. Otherwise, well, in fact, it doesn't really... Well, anyway, never mind. Case, toke, def of extern number. For example, number, let's say. stdc out number numval. Okay. Just making sure I'm understanding this correctly. Okay. So if I give it some string, as you can see, hello, it says 0. Why 0 though? Oh, break. This is what happens when you don't actually use warnings. But okay. Hello. Oopsies. There you go. Oh, why it's not actually... Why didn't it include that? What? Interesting. It should include it, no? What if I just done any character? It says A. Alright, makes sense. Okay. Okay, anyways, never mind. So we understood that, hopefully. So welcome to chapter 2 of the Implementing Language LLVM tutorial. How to use the lexer, built in chapter 1. I'm not sure though why the floats doesn't seem to be working. But anyway, let's not waste time now. How to use the lexer built in chapter 1 to build a full parser for our language. Once we have a parser, we'll define and build an abstract syntax tree AST. Parser we will build use a combination recursive descent parsing, operator precedence parsing. The latter for binary expressions and the former for everything else. Interesting. Before we get to parsing though, let's talk about the output of the parser, the abstract syntax tree. The AST. Our program captures behavior. I'll start with expressions first. Class XPRAST, public virtual. Equal default. So the destructor is virtual. Not sure what it means, but anyway. Expression class for numeric literals like 1. Public number XPRAST. Number XPRAST double val. Okay. Code above shows the definition of the base class. The important thing to note, yeah, pretty much. It's gonna be like XPRAST. To note, is using a string for the name, for the variable name. What about the value? Oh, yeah, it doesn't need that because it's just gonna be like equal to, oh, I see. Binary XPR, okay. Char operator. SCD unique PTR. XPR ASC. LHS or RHS and RHS. Both which are unique PTRs. So basically it owns them. SCD move, okay. Okay, this is for function calls. You have the callee, probably basically the name of the function, and then a vector which corresponds to the arguments that are passed, which are basically expressions. Interesting. Owned expressions because of the unique PTR here. That makes total sense, honestly. Const std string, std vector. This is all intentional, rather straightforward. Capture variable name. Oh, I see. The way to talk about functions themselves. Prototype AST. Okay. std strings. So basically the argument names and of course how much arguments there is, okay? Though, do we really even need prototypes anymore in 2023? I don't know. Function AST. The function definition. Let's have a protocol here. And it has a body. For external functions, I guess. Oh yeah, well that makes sense. Protocol and the body. Oh, sorry, not protocol, prototype. Okay, XVR AST. Makes sense. Prototype AST. That's pretty cool. Right, and count, let's go. Honestly, I guess C++ makes sense when it comes to making compilers, though it is a nightmare for anything else. Oh well, at least that's what I guess. But it totally makes sense what's going on here. Let's go. Functions are typed with just a count of their arguments. Yeah, inheritance makes things easier. Not really about inheritance. I don't know. It's like how everything comes together. It's pretty interesting. But yeah, anyway. But anyway, so functional type it with count. Type it with just count of their arguments. Oh yeah, because in this language there's only floats. There's not types. So the only thing that you need in this case is the number of arguments. It's pretty interesting. Like when we learned about creating a compiler, we could actually really like tighten the language into exactly what we need it to do, which is very interesting. Uh, since all values are double precision floating points, easily extend this stuff. Yep, pretty cool. You can. If we can, we will. Anyways, since all values are double precision, otherwise you wouldn't find me trying Vulkan and LLVM if I wasn't able to. Anyways, anything that we can, we probably gonna try. Anyways, since all values are double precision floating point, okay. In the more aggressive and realistic language, the XPR class would probably have a type field. Makes sense. With this scaffolding, we can now talk about parsing expressions and function bodies and cal. A lot of them. Anyway. Parser basics. Now that we have an AST to build, we need to define the parser code to build it. Oh my god, I have just seen that it is quite large. It will be cooked to make custom shading language using LLVM. Oh my god, yeah. But before we can actually do that, we have to learn SPIR-V, which is another intermediate representation, just like LVMIR. But then at that point, we can probably do that. That would be nice. So basically, how it would work, you would essentially make a compiler that would emit LLVM, and then LLVM can generate SPIR-V. Or you could just do it yourself, try to translate LVMIR to SPIR-V. But I think probably LVM can generate SPIR-V directly, although I'm not sure how that even works. But anyways. So it is indeed possible. Now that we have an AST to build, we need to define the parser code that builds it. Current token get this token. Provide the simple token buffer. Honestly, I think it's probably useless to actually go ahead and copy, every line from there. You know what? I'm probably just going to go through the whole tutorial. And then essentially after that, we could just get the whole code and try to run it. And then possibly try to improve it or even do it from scratch with our own way. But we'll see. I don't know. For now, yeah, let's just try to understand this. We'll start by defining static int current token. Basically, it's not current token, but current token type, I guess. But yeah, okay. Current nose token. return current token equal get token, okay? A simple token buffer around the lexer. This allows us to look one token ahead at what the lexer is returning. The current token is the current token that needs to be parsed. Error handling. So it returns an owned pointer. Why? Owned pointer to an expression. Interesting. Log error calls char str. Printf error. Then it returns null ptr. Huh. Unique ptr. Numeric literals. Basic expression parsing. So it returns the owned XPR or expression. Auto result equal make unique number expression numval. What? Oh, I see. And it gets the next token and returns the result. And returns the lexer buffer with the next token. Makes sense. For a better example, eat. This is BNF, I think, or something like that. I don't know. Get next token, and then v parse expression. If not v, return null ptr. If current token not equal to this. Okay, so that's why it's returning a pointer. I guess it's just for convenience, basically. So you could say return log error because you have to return some expression anyways. So that makes sense. LLVM or get next token right. This function is straight. A number of interesting things about parser. It shows how we use the log error routines. Expects. Okay, open parentheses. But after parsing the sub-expression, it is possible that there's no closing parentheses waiting. Should emit an error, okay? It'll return null on an error. Okay, interesting. Another interesting aspect of this function is that it uses recursion by calling parse expression. We'll soon see that you can call parse parent xpr. Recursive grammar is cool. Very simple. Parentheses do not cause construction of AST nodes themselves. While we could do it this way, the most important role of parentheses are to guide the parser and provide grouping. Once the parser constructs the AST, parentheses are not needed. Once the parser constructs, okay, cool. So yeah, it just affects basically the grouping, right? Makes sense. The next simple production is for handling variable references and function calls. Parse identifier expression. It's getting the identifier from, it's eating the identifier. And if card token not equal to that, return Mm-hmm. Arg stop pushback is cd move arg. Return. If there is no opening parentheses, then it's a variable, otherwise it's function call. Need to loop over the arguments and collect them. Oh, makes sense. Kinda zoned out at some point. Alright, makes sense, makes sense. While true, if auto arg parse expression, push back the arg, and otherwise return non-PTR. Makes sense. Expected, okay. This is some interesting stuff. This the throw routine follows the same style as the other routines. Alright, so it could either be a identifier, which is basically a variable, or a function call. Interesting. Handles this by checking to see the. Yeah, makes sense. That is very clever, honestly. I mean, it's obvious, but at the same time, sometimes you just over engineer stuff. But the actual solution is very simple. Okay, now that we have all of our simple expression parsing logic. Now that we have all of our simple expression parsing logic in place, this stuff can be confusing at first, but start to make sense when you start writing code. I already have wrote a little parser before, like AST, etc., etc. It's like a little interpreter using Python, I believe. But so a lot of these things make sense already to me. But yeah, it's pretty interesting nonetheless. Don't know how that works. It's pretty interesting. Now that we have all of our simple expression parsing logic in place, though the language that I made using Python, which is kind of like an assemblish kind of language, that was pretty interesting. Now that we have all of our simple expression parsing logic in place, we can define a helper function to wrap it together into one entry point. Call this class of expressions primary expressions. For reasons that will become more clear later in the tutorial. So a primary expression, identifier, number, parent. Parse number XPR. Now that you see the definition of this function, it is more obvious why we can assume the state of current token in the various functions. This uses look ahead to determine which sort of expression is being expected and then parses it with a function call. Now that basic expressions are handled, we need to handle binary expressions. They are a bit more complex. Okay. Guide recursion. Okay. Table of precedences. Bind up. Mm-hmm. Binary expressions are hardest part in parsing. Once you can parse expressions, like everything else is easy. Yeah, it's interesting. I never seen such code before. Uh, 10, 20, 20, 40 highest. While not is ASCII. For the basic form, we will only support 4 binary operations. Our brave is the get token precedence function turns the precedence for the current token. It is indeed brave to even try to understand LLVM. Although we haven't even touched LLVM yet, at this point we're just basic compiler stuff. Yep, yep. In fact, this is not even for the compiler, really. For now, in fact, even for an interpreter, you have to do this. This is just like the first few steps for anything, really. Having a map makes it easy to add a new operator. Or -1 if the token is not a binary operator. Oh, okay. Having a map makes it easy to add. I see. With the helper above defined, we can now start parsing binary expressions. Mm. Potentially ambiguous binary operators into pieces. So we have the first one, A, and then plus B, plus C, plus D. Okay. Oh, so this is why they need those kind of primary expressions for this stage, I guess. So if it is a primary expression, then it just doesn't touch it, doesn't care about it. Yeah. I mean, yeah, that makes sense because even variables are primary expressions. Yes. I see. Doesn't need to worry. Okay. Just start an expression is a primary expression, potentially followed by a sequence of pin-up. How did people even come up with this? Oh, well, to start an expression is a primary expression, potentially followed by a sequence of. So, CD. Walaikum assalam, MYD. Welcome to the live stream. Static STD unique PDR parse expression LHS parse primary. Yeah, I've missed though the fun, which was we were trying to basically at first we have tried to basically play with some LLVM IR, but right now we're just trying to understand how we can make a compiler. But it seems like probably better off first of all just trying to understand more about LLVM IR first, because this is basically kind of like just general compiler stuff, essentially, not really about LLVM itself, which is just about code generation. But yeah, pretty interesting. I think this is basically the front end, right? What I'm more interested into right now, I think, is the back end. But anyway, let's just go through this. But also, of course, this is interesting. But anyways, you can skip some of this stuff. Oh well, we have gone through it anyway. So takes a precedence and a pointer to an expression for the part that has been parsed. Yeah, pretty much probably to basically simplify this, instead of having to parse stuff, etc., we would probably just, like just have some AST expressions and just pass it through the like hard-coded expressions and just pass it through LLVM, etc. So, but anyways, just follow which case it returns. Okay, the code passes for A. Yeah, pretty much. I think it probably would have been better if they focused first on just, you have like some sort of hard-coded expressions and how you can do gen code for it, I think. But yeah. Just like in Vulkan, for example, too, the tutorial tries to get you directly to a triangle, which is very interesting, but at the same time, it's kind of high level, right? Like another level. Just like here, instead of, like, for example, in Vulkan tutorial, it would have been better if they just started with just clearing the screen, or just uploading some data to the GPU, or such a basic thing, but then they actually go directly to the Vulkan triangle. It just destroys you beforehand and you don't understand much. And LVM, they kind of done the same, this tutorial kind of done the same problem, which is instead of just, you have some hard-coded, let's say some hard-coded AST expressions, I guess, and then you just try to convert that into LVM IR, etc., etc. They actually, yeah, and yeah, that's pretty much it. It's like start simple, I guess. But anyway, in the next chapter, we'll start generating LVM if I remember correctly. Yeah, we'll see. We'll see. So if this is a bind up and its precedence, get token precedence. Yeah, honestly, I think I'm just gonna skip through this for now. This stuff needs a course by itself. Parsing the rest. Problem is sometimes when you skip, you just don't understand anything anymore. Anyways, yeah, I'm just gonna skim through this at this point. Driver. Because this stuff just needs, like, you sit and you try to code it yourself and see how everything fits together, right? And there you go, the whole code. Oh well. Bruh. Oh yeah, the next chapter is LVM. Interesting. Oh my god. That took me a long time just to go through it. Okay. Pretty cool. So I guess let's try now to run this and see what's gonna happen here. Okay. Interesting. Let's say x equal 5 or 35 maybe. That's good for the whole tutorial copied. What do you mean that the whole tutorial? Yeah, just the stuff that we have read so far, or that we have gone through. Not the whole thing. Yep, just the stuff that we have gone through. And no token expects an expression. Well, how are you supposed to actually do it? Oh, it doesn't. Oh, yeah, I see. So it doesn't actually do anything much now. Anyway, I didn't pay attention, I see. So generation. Well, finally, the interesting part. Hopefully, I won't regret this. Okay. Let's see. Welcome to chapter 3 of the implementing language, the LVM tutorial. Finally. This will teach you a little bit about how LLVM does things, as well as demonstrate how easy it is to use. It is much more work to build a lexer and parse it than it is to generate LLVM error code. Just as I said, it would have probably been much better. Like not much better. I mean, like creating a compiler from scratch is very interesting. Don't get me wrong, it's very nice. But I think they should have probably started with just expressions, like just the AST. You build the AST, you hard code the AST into code, and then you just go directly into the code generation. You don't go through the parsing and you let that until the end, like after that, basically, because it is the hardest part. But anyways, I mean, we could do this right now. We could just remove all that stupid parsing stuff, just ignore that for now, and just work with the backend, basically. Because parsing, and lexing, like not lexing, but parsing at least is its own kind of tutorial. Code in this chapter require. Oh, okay. Let's see. Okay, in order to draw agents. First, we define virtual code generation, code gen methods in each AST class. Virtual value code gen. Ooh. SSA, static single assignment. Register. Okay, in other words, there's no way to change an SSA value. For more information, please read up on static single assignment. The concepts are really quite natural once you grok them. Note that instead of adding virtual methods to the experience, class key, class access is a visitor pattern. Some other way to model this. Again, this tutorial won't dwell. Good software engineering practices. Okay. Alright. Well, I was so confused. I thought of true. Oh my god. Yeah, my neighbors were drilling something up upstairs. I don't know. That's crazy. All right, I think they're done now. Starts at oh, start, started to hear voices in my head. Second thing was is a log error. Lucky you, you didn't have schizophrenia. I don't even know how to spell it. Anyways, schizophrenia, right? Yeah. Oh well. The second thing we want is a log error method like we used for the bars. Okay, which will be used to report errors found during code generation, for example, use of the declared parameter. Okay, and the context. Oh my god, right now we have started on the actual LVM stuff. But he didn't say where I could get all that crazy cool stuff. LLVM context, IR builder, module, blah 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 blah. No idea. Named value builder. Okay. The static variables will be used during code generation. The context is an opaque object that owns a lot of core LLVM data structures, such as the type and constant value tables. We don't need to understand it. Okay. This is kind of like the Lewis state or something like that. Or, well, yeah. The builder object is the helper object that makes it. I remember someone in Reddit or something like that have said that it is probably much easier to just, just take your code, your source code, turn it into LLVM IR. Don't use any LLVM stuff. Just use their tools. uh, but yeah, at least for simple things, just manually turn uh, your source code to LLVM IR and let the actual LLVM command line tool do the job, basically. But yeah. Well, for all the IR we generate the module and global variables in many ways. Yeah, I could generate human readable IR. That would be easier. Yep. Yep. So yeah, I should have probably focused first on the IR, just like that, basically. But anyways, we have gone through this anyway. Rather than a unique PTR, we keep track. The nice thing about using the helpers is probably you could do all sorts of complex things very easily in few lines, I guess. Although it comes with the learning curve, I think, of actually learning how to use them first. But then I think it pays off instead of having to basically do it manually, of turning your code into LLVM IR. Okay, codegen. So look this variable up in the function. Huh? Named values name. Not sure where this variable is coming from. Oh, here it's just a map, strings and values. Okay. If not v reference verbs. Loop induction variables. What is even that? Okay, codegen. LHS codegen, RHS codegen. If not L or not R, return no PTR. Okay. So basically, if we couldn't generate code for LHS or RHS, then of course the binary expression would return null. It failed. Okay, case builder creates f at lr at tmp. Ooh. Create f at. I think that's basically the command for LLVM or something. Okay. Well, tmp. I would guess tmp is temporary. CMP compare. Okay, create UI to FP. Floating point. Unsigned integer, I guess, is UI, maybe. Get double GY, the context. Yeah, we emit code for the left hand side of an expression, then the right hand side. Oh, I see. I see. Makes sense. So first of all, we get the code gen for LHS, then we get the code gen for the RHS. Then we basically bind them together using the correct, what is it called? The correct opcode. Yes, that's the term that I was looking for. To create the right LLVM instruction. Okay. Start to show its value. LLVM builder class. Okay, RL builder knows where to insert the newly created instruction. Oh, I see. So I guess this is just for debugging actually, I think. Yeah, probably. Probably. At least that's what I understood from this. LLVM instructions are constrained by this. Yeah, pretty much. The actual opcode thing is really here. It's like the actual function that is being called. Yeah, I thought it was maybe using this, which was kind of weird. I was like, what? But yeah, that makes sense now. It's actually the actual thing is here. These are probably just optional just for debugging and having a readable LLVM IR basically. Pretty cool. And in fact, it doesn't even have to be unique as they said here. If they aren't unique, they're just gonna add a suffix number like 1, 2, 3, 4, blah blah blah. Yeah, just like we had when we disassembled that binary or that bytecode, which we just had like 1, 2, 3, 4 with no names. Yeah, I think that's probably the case. Yeah, it's basically they're saying it here. Must have the same type and the result type. The add must match the operand types. Or doubles. Okay. Yeah, I mean, in this language, right? This makes. Mm-hmm. LVM specifies that if CMP instruction always returns an IL value, a one big integer. What? A one big. Oh, a one bit integer. I thought it was a one big integer. Okay, I1, not IL. I1. Makes sense. Yeah, for example, Zig, which is LVM, you can actually just use whatever integer type you want. You can use I1, I2, I4, I256, I whatever. It's like it just you can use whatever you want. And here we go again. So annoying. Anyways, the problem with is that Scanscap wants the value to be 0 or 1 value. Ah, that's the thing, carbon as well. Yeah, it really doesn't make sense to actually. In fact, I think the next standards or like the next C versions would probably maybe add like arbitrary integer length, I guess. At least that's what I have read somewhere. I don't remember exactly, but anyways, in order to get these semantics combined, what is that? I would guess inside integer to FP to floating point. Okay. What is even that? SI to floating point. I'm not sure what SI. Signed int. Okay. Yes. Yep. Probably is. Look up the name in the global module table. The module get function callee. Okay, interesting. Yeah, okay, cool. Pretty interesting. Code generation for function calls is quite straightforward with LLVM. G18. Once we have the function to call, we recursively code gen each argument that is passed in. That is to be passed in. We recursively code gen. Okay. Create an LLVM call instruction. Yeah, we have seen that when we were messing with the LLVM IR. LLVM uses the native C calling conventions by default. These calls also call into standard library functions like sin, sine, and cosine. Makes sense. This wraps up our handling into 4 basics. Okay, so you could add more interesting stuff, I guess. Linkage, DLL, storage classes. Oh my, oh well. Look at that. Weesh. My computer is screaming right now for some reason. Even my computer can't handle this. Stochastic. Okay. Interesting. Have fun. Doesn't end. Code generation for prototypes. Functions must handle number details. The stream is dying. What? Stop scrolling. Makes sense. There for function bodies, the code starts with make the function type double, etc. TY. Get double TY. Alright. To few lines. Yeah, as you said, the prototype is basically for external stuff, or at least helps with external interface stuff. Now the value computed by an expression. Oh yeah, at this point I lost track. Alright. Changes and closing thoughts. Okay, 4 plus 5. Define double. Okay, entry reds double. Nice. Find double foo, double A, double V. So yeah, notice that instead of having that 1, 2, 3, 4, blah blah blah, right now we have actual nice stuff. Actual names. Pretty cool. So diff foo AB, which of course returns double. So define double foo double A, comma double B. Multi-MP. Yeah, this is the things that I've talked about before. It's just for debugging, for readability. Fmol, double AA. Yeah, pretty much like assembly at this point, right? And pretty cool. My cool GIT. Oh yeah, it was this long because there was the code included. So I was like, bro, let's just skip all of that. So yeah, they shouldn't not include the code here, honestly. I thought there was more to read, so I just skipped through that part. Anyways, just a little rant there. Okay, now let's see this up. So build up that guy. And it's weird that we're using LLVM itself. Oh, what? Note forward declaration of LLVM AP float. Here we go. Problems. Oh, I think maybe I have to link LLVM or something like that. Hold on, I didn't see the actual command that they used. They're using some LLVM config stuff, which I have no idea. Oh, I could just call it directly, actually, yeah. I could just call it directly and just copy the flags. Although, it may be possible using CMake directly, I'm not sure. But yeah, this is pretty much what we need. Yep, you link with LVM16. You set the include and where to find the library. Though, what if I just linked LLVM16 instead with no crazy stuff? And it seems to be using C++17. Interesting. But anyways, where is it? Target link libraries. Project name. Okay, LVM16. So private. Time of truth. Oh, there we go. Same problem. Okay, I think I'm not looking into the right tutorial. Oh, what? LLVM 18? What the are you talking about? Okay, hold on. I know what to do, I think. Let's see. Okay, hold on a second. LVM 16, 16 bucks. I do have LVM 16, right? Yes, 16. So yeah, make sure to go with the version of your own thing, I guess. Not here. Go to documentation. Oh, actually, maybe I can go to the download page, maybe. And then possibly to my version, which is 16. Yeah, here. And documentation. There you go. Okay, so right now I'm in version 16. Let's see. Getting start tutorials. Okay. And where we was here, I think. Yeah, this chapter. And go down. There you go. And let's hope this actually works. Hey, this tutorial for every version? That's cool. Yep. Well, at least seems like. Oh my god, still the same problem. Well, maybe because I didn't actually include everything? No, I mean, there is... Weird. Where are the problems though? I don't see them here. They should have popped up here. Just copy all these flags. I mean, it's not as easy. Like, well, let's just use honestly the what he's using here, honestly, and just call it a day then. Yep. Pretty much Clang instead of using CMake. Okay, so it's called main.cpp in our case. Dash o toy. Okay. Main.cpp not found. What? Oh yeah, because I'm in build for some reason. There you go. It actually worked. Nice. Now I got the toy. The toy. And there you go. Okay, cool. So 1 plus 3. Huh? Okay, I had to actually do that. Okay, cool. Okay. Ret double 1.0. 1.2. Yeah, I just computed it. Interesting. Maybe sine. Oops. Well, we got some error. Nice. Some error stuff. What? Oh, I see. Then maybe sine of 1. Oh, oops. What am I even doing? And known function reference. Oh, yeah. It's not actually linking to the standard library, maybe. Okay. How do you even define functions? Let's see. Find out. Well, that's weird. Oh, you actually say extern first, maybe. Okay, hold on. Oopsies, what I have done there. So extern sine of A. Okay. I rate. Okay, nice. All right, let's go. So you just say extern sine of 10 and yep, exactly. And you just call it then. Interesting. Let's go. Return double call temp. But yeah, honestly, as you can see, it's quite complicated to get into it directly. So it's probably better for me to just focus on the LLVM IR for now. So yeah, that's probably what I'm gonna do. Yeah. Let's see what other chapters there is. There's code generation, so we have done this. Now, next up, it would be just adding GIT and optimizer support, extending the language control flow, blah, 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 blah. Extreme laziness. Per function lazy compilation. So GIT is all about laziness. Add in optimizations and introduction to ORC layers. Who said that lazy is fast? Starting out with Kaleidoscope GIT. Okay, let's go to the last chapter. What's happening here? Interesting. I wonder how much code it is, the whole thing. Well, we gotta know now. Well, is there anything that have changed, by the way? Oh, there's this stuff right here. I guess, maybe, but anyways. See ya later, see ya, Ridwan. I'm also about to stop the stream, but see ya. Have a great day or night. Okay. Just gonna try this up, I think, and I'm gonna stop the stream at this point. Main driver code. Okay, so it's 1,400, well, 1,400 lines, right? Around that. Pretty cool. So if I run this up, oh well, never mind. Let's actually run it through that command. Let's go. Oh yeah, let's call this joy.cpp for a second. And yeah, oops, cancel. And let's try now. And let's go. Oh, it's actually a fatal error. Include kaleidoscope GIT file not found. Oh well, it seems like they have some other code that I didn't look into. But anyways, so I think that was it for this video. It was an interesting stream. It was an interesting experience. That was it for this. I pretty much enjoyed where we actually explored ourselves, the LLVM IR, and that's probably what I'm gonna do in next streams. Hopefully, but we'll see. So that was it. Thank you for tuning in and see you later. Goodbye, everyone.